Balancing of rotors. So let's consider that we have mass, we have a body which is unbalanced, and properties of such unbalanced body are m, so it is a mass of unbalanced body, y, c, z, c coordinates of center of mass, so we mean that somewhere here there is a center of mass, and for solution, for balancing, we need to know only y and z coordinate with respect to this system. There is a rotational axis, A and B rotational joint. So then we know Jx, it's a moment of inertia with respect to x-axis. Then dyx, dzx products of inertia. So these are properties of imbalanced body. Properties of imbalanced body. And as it is imbalanced body, we make some difference between properties of balanced body. So all properties of imbalanced body will be denoted with prime. Okay, so we have properties of imbalanced body. This is imbalanced body. So the process of balancing starts with defining the balancing masses. So we consider that we have two balancing planes with distance denoted by A1 and A2. So this is A1 and A2. So this is a position of balancing plane 1, and A2 is a position of balancing plane 2. So this is balancing plane 1 and balancing plane 2. And to this balancing planes we add balancing masses. So there will be balancing mass M2 on diameter R2 under angle phi2, and balancing mass M1 on diameter R1 under angle phi1. Oh, sorry, it must be here. Yeah, it's located, the beginning is located here of this diameter. It starts here. So the process of balancing ends with calculation of these parameters. So we need to calculate R1, R2, Phi1, Phi2, and M1, M2 if we want to make a balancing process. If we have this, if we know this, so we can say that we have balanced body, and I can make a new image only for illustration. So this is unbalanced body, this, and there are balancing masses. So this is balancing mass 1 and balancing mass 2, and so this is M1, M2, and this all is balanced body. Balanced body. Okay, so parameters of balanced body is mass, M is a mass of unbalanced body plus balancing mass 1 plus balancing mass 2. Another parameter of balanced body is static moment. So mass, static moment. So static moment xy about x is, oh sorry, it's not about x but it is with respect to plane. So it is m by zc plus, so it is mass of unbalanced body by zc, and zc is here. There is center of mass and there is zc prime, yc prime. So we consider z coordinates. So center of mass is on zc coordinate plus, and z coordinate of m1 is r1 by sinus phi1 plus z coordinate of m2 is r2 by sinus m2. Another static moment is szx. So it is m by yc, and we consider y coordinate. So y coordinate of m1 is r1 cosine phi1, here r1 cosine phi1, and y coordinate of m2 is r2 cosine phi2. And Another properties of balanced body is products of inertia. Products of inertia. So we have dxy is dxy with prime plus, and mass m1 has a product of inertia it is a1 by r1 cosine phi1. So if we have x and y coordinates here, so x coordinate of m1 is a1 and y coordinate is r1 cosine phi1, and the same with m2. So it is a2 r2 cosine phi2, and finally we have dzx. So it is a product of inertia of balanced body. It is composed from product of inertia of unbalanced body plus z and x coordinate of m1 by m1. So z and x coordinate. So x coordinate are a1 or a2 and z is with sinus. So it is a1 r1 sinus phi1 plus m1 a2 m1 sinus phi1. Okay, so there are some properties of balanced body which is made up by unbalanced body and balancing masses. So now I'm going to draw a free body diagram. Of the case where we consider of balanced body. So it's quite easy because we already know how to draw free body diagram of rotating body in 3D. So there is a coordinate system x, y, z with 0 origin, and we can draw in these directions r, a, z, r, a, y, and r, a, x, and here in B joint r, b, z, and r, b, y. Apart from this, there are moments, D'Alembert moments, so there are mdz, mdx, and mdy, and moreover, if we consider there is a center of mass C, so we look at the projection of center of mass, and by this projection we lead O force and T force. These forces are perpendicular to each other, and we consider this direction of omega and the same direction of acceleration alpha. If we know coordinates of center of mass, we can calculate this angle. This angle is beta, and it is this angle beta, and this is E, this displacement, this, yeah. And now we are going to write the equations of dynamic equilibrium. There will be 6 equations, so it is 1, 2, 3, 4, 5, 6 in direction of x, y, z, and about x, y, and z. So in x direction we have the only one equation. Rx is equal to 0. In y direction we have Ray plus Rab plus O by cosine beta plus T by sinus beta is equal to 0. In z direction we have Ray plus Raz plus Rbz plus O sinus beta minus T cosine beta is equal to 0. Moments about x. There is only external moment, ME, so let's say that we have some exciting moment, ME, external moment, plus mdx is equal to 0. Moments about y axis, they are Raz by, let's say, LA, and LA is this distance, LA, and LB is this distance. So we can continue with minus this plus Rbz by Lb plus Mdy is equal to 0. And moments about z. So it is Ray by La minus Rby by Lb plus mdz. So we described the system by 6 equations, and now it is very easy to continue, because we can say, apart from this, because from this follow that Rax is 0 in for all cases, so we can continue from the second equation. So we can write that Ray plus Rby is equal minus O cosine beta minus T sinus beta. Third equation, Raz plus Rbz is equal minus O sinus beta plus T cosine beta. Four minus La Raz plus Lb Rbz is equal minus mdy. Oh, sorry, I continued with fifth, so this is sixth equation. So it is La Ray plus Lb Rby is equal minus mdz. So this is some clue that if we consider that O, D'Alembert force, is me omega square and T is me alpha, so if E is equal to 0, so it means that center of mass is directly on axis of rotation. So from this follows that center of mass lies on axis of rotation. So this is axis of rotation. And from this we can somehow deduce that for balancing we need to have E equal to 0, so we need to have center of mass directly lying on axis of rotation, so C must be directly on this axis. So we lose some excitation given by D'Alembert's force, by normal and tangent D'Alembert's force. So this is important condition. And second condition, so we know that mdy is alpha dxy minus omega square dxz, and mdz is alpha dxz plus omega square dxy. And if this is equal to 0, it's also some clue that we lose some excitation, so this will be equal to 0. Okay, this right side, so we lose some excitation of the system. And if it is rotating, so omega is not zero and alpha also may not be zero. So from this follow that dxy should be equal dxz, and it should be equal 0. So these are two important conditions of balancing. So we have some requirements for balanced case. So this is first requirement, and this is second requirement. And we say that first requirement represents a static condition for balancing, and second represents a dynamic condition for balancing. Okay, so we have static and dynamic conditions for balancing of body. Static condition is that center of mass must be on the axis of rotation, and dynamic conditions are that products of inertia must be equal 0.